Guys, in this 2 weeks, we focus on the coding. The software we will use is a MATLAB. I believe all of you have already enrolled, or most of you already enrolled and passed the course, which is called as an advanced structural theories. So you should have the basics idea or the coding skills by using the MATLAB. In this assignment, and if you have some of the senior, you got the friends who have learned this course before, these three of the structure is the most popular one that I use and to test you guys, right? And this year I didn't change much of the structure, so I just changed the dimension. So the reason for this, I want you to practice. Just give it this way. For all the assignment that I give it to you, and in my part, there is no exam. You just submit the full report. You submit some of the MATLAB code for me to check up. I want you to have some idea, which is the link between the theoretical that you have learned and you have done all the calculation. You know the basics idea where the finite element is coming from, and I want to link you to the another world, which is rather than you just keep using the package. I like you to learn and looking at how the package works. And the package that I use and I like to teach is a CALFEM, CALFEM, developed by, I think, by Lund University. And let me show you later on. And the CALFEM is very good. The package is very simple and it's very clear, transparent between the coding to coding. They got the different function. And the task that I could share with you today is I will show you how the formulation that you have and the basic formulation that we use for all the time for the elastic analysis, but the structure we're looking at, we use an isoparametric finite element, which is based on the displacement fields. You know displacement field exactly. How we use this to model what is called a plane stress and plane strain structure, right? And the problem task that you're looking at, this is from some of the classical one. So what is happening here? We had the notch. The notch is mean it's a tensile test. Remember you did in the material test, or if you haven't done so, it is a tensile test. So you have the materials which is in the rectangular, and we project them in the plane because we didn't want to model in the 3 dimensionals, and we can sometimes we assume them to be the plane strain and plane strain. I believe you have the concept of the plane strain and plane strain before. If you didn't have so, let me know, right? So I can quickly explain to you. We can try in our modeling, the way how we work is that we try to model the sophisticated structure which is lie in the 3-dimensional space, and we try to looking at them in the simple way, but we didn't lose the accuracy as much. So what we can do on this, we have to use some as an assumption. Most of the assumptions that we make, we have to look at the boundary condition, right? When every time we talk about the analysis, we keep talking about the most important part is how can you just think and model the boundary conditions correct to make your problem, which is in the 3D space, or the shapes look very much difficult, to be as simple as possible. If you can do this, you can analyze or you can just predict the behavior of any structure in the world. So there is no such a form that you cannot do, right? So in this case, we just use a very classical and very simple. So basically, in this type of the structure, if I draw them in the 3-dimensional space, so it's got the depth which is come with them, right? It's got a thickness. But because what we know here is that in this 3-dimensional specimen is really thin. When we talk it's very thin, so what we're saying that the stress in the perpendicular direction is 0, because we're saying that we allow the stress to transfer only within a plane. So it means we try to project the structures within the 2-dimensional plane. And in this plane here, we're saying that the stress in the perpendicular direction to the plane is equal to 0. So that's why I'm saying that the sigma, which is the stress in the XCS is right, which is perpendicular to the plane. If I assume that the plane lie in the direction of X and Y, and the C is here, or some people call it as a set. we say that in the perpendicular direction, the stress equal to 0. This also include all the shear stress, which is including the XC and YC. So 3 of these terms, the stress are equal to 0. And this is work for the very thin structure. The thin one is like the plate structures, right? And we know there is no forces applied in the different directions. So the force only allow to apply within the X and Y's coordinate, right? And we call this structure, and we can simplify them as a plane stress, right? So I remove this. So I just model them as a plane stress for now by making and have to ensure this assumption is correct. And by doing this, we can reduce the number of variables. Remember that in the stress tensor, you learned the stress tensor concept already. We have, so what we have here for the stress tensor, we have the sigma xx, we having the sigma yy, we having the sigma c, right? We have the tau, which is the shear stress xy. We got 6 terms of this for the 3-dimensional problems. YC, and we having XC. So if we know that we can make the simplified assumption, so we're saying that, okay, in the plane stress, I can simply say that the value of these unknown variables, because it's in the perpendicular direction, they all go to 0. So by having this, I can reduce the space of the stress tensor from the 6x1, right? Because in this, you got the values for each of the element 6x1, right? To reduce is to become 3x1, right? I draw them in the columns. So this will reduce all the metric as well. Remember, you have the Hooke laws, which is the Hooke equation, which is to tell the elastic stiffness, right, in terms of Wolfram ratios, in terms of the Young modulus, right? So that will reduce from 6x6 to be 6x1. And of course, you have to justify first that this assumption is correct, right? So the first problem is this. Listen to me first before we go ahead. We have the notch specimens, and we apply the uniforms. Listen to me. This is the uniforms tension force, and in terms of the alpha, right? And what we do here is that I assume that the thickness of this is so thin, so that's why I take it equal to 0.1, right? We have to use this in our calculation when we take the integration over the volumes. And what is happened is that the forces that we have here is a total force along the line here, right? So if when you do the calculation, this is the total force. Keep in mind, once again, this is the total force. Right. And you have to do the structural discretization, and we keep talking about this later on. And what we do is that we have in this two-dimensional plane, which is in the plane stress, and we have the problem that there it is symmetric over two of the axes, which is the over the x and over the y. Right. In this case, you don't need to exhaust in modeling this structure in full. In full, which means you have to model them with the full notch. It is not quite wise, or it's not quite smart way of doing this work. To my suggestion is that if we define that the loading is symmetry over the y-axis, the geometry of the problem you're looking at, it is also symmetry over x and y. So you know that the behavior will give you the mirror image. The mirror image is mean what's happened over here is similar to what happened over here, but it's in the opposite side, right? And what happened over at the top will be similar to what happened at the bottom, but it's just the mirror image of each other. So it allows us to just model this problem in just a quarter, right? When we talk about the quarter, so I just only model this only this part, right? So that's why I give some of the indication of the initial mesh. You have two choice of to pick the mesh. You can use 3 node or you can use 4 node. In this assignment, I asked you to use just the 4 node isoparametric problems. I'm sure that you learned the concept of the isoparametric, right? So you model this problem as a 4 node. So what you do, right? You just take a quarter of this problem and you draw the boundary. This is the boundary line of what you have in the problem here. And before you discretize, so discretize means you subdivide them into the small number of the element and you connect them to the node. The information that we use in the connection is the displacement at the node, right? You have to indicate what is called the boundary condition first. Look at the boundary conditions here, right? We have the notch. So the notch is mean at this boundary is free. So it doesn't have any constraint, restraint at all. But along the boundary here, which is respond to this part, it's got some of the condition. The condition that is append to this is that it doesn't allow the movement because this is in the symmetry lines, right? The movement in the x-axis, but it's allowed the movement in the y-axis. So that's why when I want to put the boundary condition, so what I do, I just simply put the direction of where I like to restrain the problems. So I restrain the movement in x, which is I saying that dx along these directions here is equal to 0, right? Because it's at the line where you have the symmetry. You got two of the symmetry lines. One is in the centers, and the other one is in the middle. So this is the x, and this is y, and all they are symmetric. Right. So I just try to indicate the boundary condition such that when I take this back to the original problems, it can indicate the real behavior of the problem we're looking at. Then I'm looking at the boundary line at the bottom. Similarly, it's just like over the symmetry in the x-axis. So what is happening is allow the movement in x, but it doesn't allow the movement in y because anything that move here, it will affect the thing at the bottoms. So that's why I put them here as a boundary condition as a whole. And the boundary condition at the bottoms, let me just so what the indication is that the movement in the y directions in this along the bottom lines or at all the node that we're looking at is equal to 0. So you would have this node, you restrain them the movement in x and y axis, right? So we already indicate the boundary conditions, and what the last what we do, you have to put the loading condition as well. The loading condition to what we have is half of this force. So what you do, you apply the force and the sum of this force had to be equal to half, which is 0.144 alpha, right? So you might see that when I put the length of the arrows, I put this half of this because if you're looking at in the tributary area concept, very simple. If you have the UDL applied to this, and you take the load here, divide by half of the depth, which is 1 meters, right? Or the unit we look at is kilonewton meters. So basically, when you use a tributary areas, this go twice of the areas than the loading at the edge of the problem, right? And you apply the force. The less of them, you just need to discretize a problem. How we discretize a problem is that the first thing of all, you have to allocate a node. I start to discretize, so I start to split the whole mass that we're looking at. I allocate the boundary already. I split the whole mass and I start to assign the number of the node. I start to assign the number of the element and the connectivity of the member, right? So what we do, I just take the node first. This is all the node we're looking at. Assume that we have the uniform mesh, right? So you just make in an order. The only thing that you have to keep in mind is that the ratio between the width and the height of the mesh cannot go above the ratio of 0.5. So what it means is that when you should not have the stiff mesh. What it means for the stiff mesh, because we made a poor condition to your analysis. For example, if I'm looking at the mesh dimension, the best idea is you just try to control the dimension of the mesh in the proportion of A and B. The best idea is we should try to have this equal to B as much as possible. If you want to have A more than B, right, you should not have A more than twice of B. Or if you want to have B more than A in terms of the dimension, you should not have B more than twice of A. So this is not allowed, right? So that you have the good condition of the mesh. And I think you might learn it before. And this is we call as we're looking at the geometry of the mesh, so that we don't have and you don't go to experience with the poor condition of the results. And after that, what we do, you just do the connectivity. So let's looking at how we connect them. Normally, what we connect, we use an isoparametric. The idea of the isoparametric, so it's a dimensionless property of the mesh. When you have the dimensionless properties, so what has happened? It doesn't look the width or the size of the mesh you're looking at. It just treat them as a unit, one and one, right? So you start from the mesh, and the thing that is only care of is how you orientate the order of the mesh in the element. So, right, the direction that you start at the start node, and you keep rotating the node to form the rectangle elements, you should follow the same order for all the mesh you're looking at in the problems, right? If you go in the anti-clockwise direction, you keep going anti-clockwise for all the member. But if you start to go from the clockwise direction, you should keep using the pattern of the clockwise direction for all the member. So in my style that I do the problems, I always go in the anti-clockwise, and I always start the node from here, and I count 1, 2, 3, and 4. And the order that you start the node, it doesn't matter. You can start the node at anywhere. It doesn't make the problem at all. You still have the good, nice, the similar stiffness or the equilibrium equation, or sorry, the strength equation. But you just need to follow the pattern of the anti-clockwise, or if you want to go for the clockwise, you go for the clockwise, right? And you can start at the node number 1, or you can start at the node number 2. It doesn't matter. This will give you the similar strength equation, right? This is the basic property of the isoparametric problem, and it's a very nice problem, very, very nice property. So that's why we use isoparametric mesh rather than we use a quadratic mesh. The quadratic is a 4 node, but you don't scale them. So you don't use those, it's called the unit length of the element you're looking at. So if I stick to the pattern when I want to connect the nodes, so I call them, this is the connectivities. The connectivity is when I start to tell the programs, or I start to construct the matrix according to the node where I start from. I start from the node 1, go to the node 2, node 3, 4, and finish at 1, right? So I cross up the node. So what the matrix need to know, the programming need to know, is that they need to know where you start the node, and how you rotate them for 4 other nodes. The last one you don't need to tell, they will close up for you automatically. Right. And as I mentioned before, if you're not sure, you follow the pattern to what I use, which is the anti-clockwise, and you keep doing. Then what has happened in this case, right? I show you, I start the mesh from the node number 1, node number 2, node number 3, and close up. I got first element, node number 1, 2, 3, and close. I got mesh number 2. So I keep doing this until I can assign the element as a whole, right? And this is the 4 node element. So you might see that the pattern when we start to construct the mesh is just repeating. So it means you just keep doing the same routine for all the elements. If you need to have 100,000 elements, is it possible that you have to do it by hand, right? You have to write some little code to ask the computer coding to split the element for you. And this is the job that you have to do in this assignment, right? But what you see here, according to if I keep doing this way, I start the node here, come second, third, fourth, finish up. So it's keep repeating as a routine. So when we have the routine for the construction of the mesh, so this is good for the computer because the computer like everything in the routines. And that's why the finite element method has been well popular in the last 30 years because we have the PC, which is the personal computer. When we have the personal computer, anyone can write a little code by yourself, and you can construct the approximation method, which is the finite element method, or the discrete models, right? So that's why more or less the research in the last 30 years, they're not looking at the closed form formulation at all. They use the approximate form for the solution. And the finite element provide the approximate forms, right? So I keep doing this. And if I use a routine, right, I just put into the computer and I say, okay, we keep doing this for repeating pattern, then I get all the mesh in the element. When I have the mesh, so basically I know exactly that, okay, this is the mesh, the element number 1, element number 2, element number 3, 4, right? I keep running the number. I know this is 5 up to 8. So you're seeing that you can use some of the simple calculation to tell the number of the element and the connectivities, right? If you use the pattern that is repeating. And if I tell this is the node number, I say this is the node number 1, 2, right, 3, 4, 5, and keep running the number 7, 8, 9, 10. I keep doing this, and you can guess, right, how much you're looking at. This is 15, 16, this is 20, this is 21, this is 25. And you said you want to look at, okay, what happened with my element number 1? Let's have a look here. I just list them in the matrix, sorry, in the table. I'm saying that this is the member 1 and how the connectivity is looking at. So I'm saying that, okay, I'm looking at the member 1, the connectivity is starting from 1 to 6, 7, I close at 1. The element number 2 is starting from 2, 3, 7, and 8. Number 3, 3, 4, 9, 8, 9, right? And number 4 is starting from 4, 5, 9, 10. And you're seeing that all the elements that sit in the same rows is come with a repeating pattern. You see that you can guess by without looking at how the geometries look like. If I'm looking at the number and knowing that it's running from 1, 2, 6, 7, I keep increasing by 1. So I have 2, 3, 7, 8. I add 1 for all the number. Here I got 3, 4, 8, 9. If I add 1, it's give me the 4th element, which is 4, 5, 9, 10. So by looking at this, you can make a repeating pattern in your coding, right? And this is in the same row, the element in the same row, number 1. That's why the computer coding is very much well popular, because you can just make little piece of code to ask the computer coding to just generate 100,000 mesh for you by using this repeating pattern. Okay. And what you do after you can generate the mesh, you tell, okay, how many mesh you have, you tell the boundary condition, right? The boundary condition, how we tell them, we looking at the degree of freedom. Remember, when you're looking at in each of the element, you got 2 degree of freedom, right? Each of the node that is come with them is got 2 degree of freedom. Then you just tell which one the degree of freedom it has been restrained. For example, in this case, the degree of freedom to what I put another colors. For example, if I put the color in the yellow, so this is mean I restrain them, right? So I keep telling, this is how I indicate the what's it called, boundary condition. And you can tell as well where the loading apply, right? So the loads always apply at the degree of freedom as well. And don't forget, this has been restrained in both directions here. You can keep doing this. So all of these that we have here, we call them as a mesh construction. So you start to model first. How can we start to look at the 3D problem? You just simplify them to be the 2-dimensionals. And then how can we just try to minimize the efforts of our modeling? And in this case, we have the symmetry in 2 direction. Then I just take a quarters, and then I just looking at for each of the quarter and looking at for this problem, how the boundary condition I'm looking at for each of the lines, so that when I bring this problem back, it still give me the response as a whole, right? And start to discretize. When I discretize, I allocate the node first, and then I start to connect node to node to form the 4-node element. And the way how I explain to you now, we call them as a mesh construction. Okay, and the computer coding will use this information to assemble the matrix, to construct the matrix for you, and we will discuss the matrix later. In this case, in this first problem, thing that you need to know is that the loading that we apply, we have around 6-7 group. The load has been changed. Each group, it doesn't have the same load, because once again, I trust that you do the problem by yourself, but I want to see the variety of you. So I didn't want you to come with the same number. So that's why the loading you have is all of them, they are different. Okay, keep in mind, you don't have the same results. You have the different value of the loading. Okay, any problem first before we move ahead? No response. All right, so this is the first problem, which is the most simple one. And what I brought to you here, this is just the first time that I like to show you. This is taken from my paper. I have put the reference, which is coming. You can read it through, right? This is some of my research, right? I have probably some of the recent paper, right, last year. And this is some when I was as a professor at the UC of New South Wales. So I published this paper, and I used some of the very advanced finite element to solve the problems. Okay. When we're looking at this, the question that you have next is that what you should do, right? So you already construct the mesh and so on, then you need to look at the formulation. The problem that we ask before we go to the formulation, the problem they ask is that according to the law that we have here, the unit is a kilonewton meter, so you don't confuse with the unit, right? You have to transform anything to be kilonewton meters, including the thickness. I use it 0.1 meter is a 10 centimeter. I brought to you here what I expect to see when you apply the force with this type of a boundary condition. There will be the displacement that corresponding to the applied force. This is in the function of the applied external force, which is the F or P. Right, when there is a force applied here and you have the restraint condition at this directions here, you're seeing that along the boundary line, it doesn't move or it doesn't translate in the X direction at all, because we fix them, but it can move in X and Y. But along these directions here, it doesn't move in X and Y, but it can translate, so it can slice, right? Except the node here in X direction. This is the deformed shape to what we expect to see. What is happen if you have the thin sheet, you can try with the paper and you just have the square paper if you want to test for yourselves, and you just make the notch. So you just cut a little bit here, this half, cut to the half, and you leave this part to be bonded together, and you just pull the paper slightly slowly to the sides. So you apply the tension to the paper that you try to experiment by yourself. This is the plane stress, and you'll be seeing that the more that you try to pull the paper, you see the deformation of the paper is before we deform like this. And that tells the behavior of the plate, of the thin plate, right? And if you want to looking at how much of when you apply the force, how much of the stress is distributed through the body of the structure looking at, this is the plot of the allocation of the stress distribution. In your assignment, you have to plot, this is called as a deformed shape, and you also need to plot in color, which is called as the distribution of the stress. Right? And the stress that I like to looking at, we call them as a von Mises stress. Right? And this one, we call them as a von Mises stress. The von Mises stress is the material property, the formation for the material property that has been used for the ductile material. For example, we can represent the steel structure or the steel material by using the von Mises stress. I'm not going to go to the detail what the failure line of the von Mises, but I give you the formulation. You can use this formulation to explain, right, to describe the von Mises stress. We have the plane stress and the plane strain, and the formulation of them will become as a positive sign. You have to take the square root, right? You just substitute the value of the stress tensor that you find, right, according to each of the Gauss point. You know the Gauss point already, right? We use the integration rule, which is the approximation. So that's why you need to have the Gauss point. And you substitute them, you get the values of the von Mises at each of the Gauss point. When we talk about the full node, right, the thing that we should know as well, let me move. Let me move this. So that you have some of the theoretical backups here. And I want to enlarge this diagram. It's not look very real. So when we're looking at in each of the element, we call them as a generic elements, right? When we use a Gauss integration rules. So what we do is that we split the problem, the element to be 4 parts, and we represent the values of the stress at the Gauss point, which is at the Gauss coordinate. You have the Gauss coordinates here, right? So you already learned what the Gauss points mean, which is we use to approximate the integration, right? Because when we form the finite element formulation, we have to use the integration, and we cannot have the closed form integration, so that's why we use the integration rules, which is the approximation, and we use a Gauss quadrature. Quadrature is mean 4-point integration rules, right? So we have some of the formulation that I will recap today's, right? And more likely you have to do the coding of this, but don't be scared. I have some little piece that can help you to do the coding. I'm sure many of you may have talked to some of the senior or those who have sit in the class before, and you may have some other coding in your hand, but please, I'd like you to have some practice. So don't try, right, for the sake of your learning, not my learning, is your learning. I hope that you will do the assignment by yourself, right? So don't try to use any past materials. But I provide to you as much as possible already. You don't need much of the code, right? You just develop some little piece of code, and I hope that you enjoy in writing the code, right? Because it's just train your brain. Okay, so we leave the first problem for the time being. So you should understand what the problem we're looking at for the first structures. Then we move to the second structures, which is a bit different, right? And this is the classical problem as well. We call them as a punch problem. The punch means we have the uniform distribution and we push to the body of the structure. So we push down, and what we do, we assume that this is the infinite, right? The infinite depth of, when we talk about the infinite depth, so what I try to say is that the infinite depth is mean if we are looking at in the depth dimensions, we have the depth of this problem to be infinite. When we have the depth of this problem to be infinite, what is happen? We can assuming that once again this is the in the x and y's coordinate. You can give the coordinate somewhere here. Right, and you have the c direction as well, which is in the z direction, which is in the perpendicular to the plane. And if we have the problem which is having the depth to the infinite, so what is happening here is that the strain in the perpendicular direction, which is the strain in this direction here, is tend to be very small, right? Because this is go to the infinite depth, right? The thickness is so deep, right? And we call them, this is the plane strain. The plane strain, what the condition we have here, we're looking at the strain by itself, right? The strain we have in the perpendicular direction, we have the strain in the c direction, which is equal to 0, right? We having the shear strain in the perpendicular direction as well, equal to 0. And the last one, so this is the condition of the plane strain. But keep in mind, for the plane strain, it doesn't always saying that the stress in the perpendicular direction is equal to 0. It's not always, right? You have to keep in mind. It's not true. The only thing that is true is the strain condition. And you can use this strain condition as substitute back to the Hooke laws, right? Which is the stiffness equation for each of the elements. And you can just simply manipulate them so the Hooke equation can reduce from 6 by 6 to be 3 by 3 by using the condition of the plane strains. Then if I can model them, right, listen to me first, as a plane strain. So basically I cut a slice of the plane. So I taking a slice of the plane. So what is happening is that I only look this slice of the plane, right? I taking a slice of the plane and I do the modeling of this. Then I can just simplify the problem from the 3-dimensional space to be the 2-dimensional space. And what we do, once again, I start to simplify the problem. So I'm looking at first, is there any the symmetry lines in these problems? And I found that yes, there is. When there is a symmetry lines here, so what I know is that is symmetry about the y-axis. So what is happening? Any half behavior in the half of this will be similar to the other half here. So that's why it's allow me to model the structure only half of the problems. So I only go for half of this. When I deciding to go only half of this, then I start to looking at, once again, what is called as a boundary condition. When I'm looking at the boundary condition, right, so I take half of the problems. So I start to discover what is happening over the symmetry lines, right? The symmetry line, what is tell is that the movement, right, the node movement along the x-axis is equal to 0, but it can deform in the y-axis. So that's why we have the conditions over here to restrain the movement of the node along the symmetry lines. And I'm saying that the movement in the x direction equal to 0. And similarly, I'm looking at the bottom. At the bottom and at the sides here, what it's telling me is that this one has been fixed along the edge of the boundary point we're looking at, right? So when we talk about the problem, this is the support side. So it has been supported by at the bottom surface and at the right-hand side, and of course at the left-hand side surface as well. And when it's provided a fully fixed support, so what it means it restrained in both x and y direction. So that's why the boundary condition at the bottom is have been restrained in x and y. For all along the edge of the problems here. And I simply call them that the displacement along this edge equal to 0, and at the bottom one as well. Right, so I already defined the boundary conditions. Then I'm looking at the loading condition as next. So what we do, we have the uniform distributed load, which is covered over the area here, and I tell this is the length of the loading that has been applied. And you see that over the length of 2 meters, and the total force is equal to 2 alpha. Once again, alpha is the number of your group. If you are the group member number 1, so the load, the sum of the force is the total force. Right, equal to 2. Then you model only half. That's why the loading you look at just half of this. Okay, and you just have the loading. Apply them as a UDL over the areas which is we take into account of 1 meters. Right, the length of this is depend on how you want to discretize the problem. And once again, we use the same rules. So you first allocate the node. Simply just tell how many nodes you want here, and you can on what happened. Not good. So you allocate the node, right? Each of the node will tell the information on the degree of freedom. Remember, you learned that before. Each of the degree of freedom, if the node give you how many degree of freedom? 2 degree of freedom in the plane which you have in x and y. Right. Then we talk about this degree of freedoms here. This has been restrained. Right. So in this one here, we have the nodes that are freely in the vertical, but in the horizontal direction, it has been freeze. So you have different types of the degree of freedoms, right? So the one that I draw in the yellow or the what's it called, the brown colors. So I indicate that this is the restrained degree of freedom. So it doesn't have the movement. So it's at the support, right? Then you can construct the element by make the connectivities. The connectivity, what it means, you can just simply, I don't know what the color I should use, connect the line, right? The node to the node, and then you get each of the element, and you keep repeating this And if you just extract the number of the connectivities, you will have the pattern of this, right? Then you can construct a mesh. And the second problem is the punch, which is the standard. This is the stress. What I try to tell is that this is the stress. If I cut, no. If I have the value of the force applied over the area here with the loading of alphas, so I will see the distribution of the stress. This area will be the high value of the stress, right? And how it's look. So it's try to push and pull oversize of the loading. So this is one of the very classical soil problem that we may looking at. One, and this is the distribution of the von Mises stress. The von Mises stress that I'm looking at in these problems I give you the formulation for the plane strain, right? You just have the stress tensor in X, in Y, and the shear stress, and you substitute them for each of the Gauss point, you get the value of the von Mises stress, and you can just use some of the function to average the stress in the element, right? So they can give you the product for the distribution of the stress. Okay, any problems? Don't forget, this is the loading you're looking at. Okay, the last one is the most difficult one, right? This one I took it from the real problem, right? This is come from when you have to design the concrete gravity dam. So let me show you what it means for the concrete gravity dams. You're looking at, this is the dam. I try to draw them well, but please bear with me. Right. Right. So you have, this is the concrete dam. So what I try to draw here, I try to draw each of the cut that we can have a slice of the dam. Right. So what has happened, we have, this is the concrete dams. Right, this is at the crest top. And you have the water, and they try to restrain the water to keep the water, right? So we call this side as an upstream phase. And at the bottom, we call them as a downstream. And you have the water levels. This is right? No. Okay. Hope is look okay. And you have the waters at the upstream side. Sorry. So it's keep the water at the upstream side, right? So this is the amount of the water that has been kept, right? So what has happened, right? If we models have a look here, If we try to model this concrete cavity, then we have two other choices. One, you want to model in the full three-dimensional space, but you will have to use a very high computing effort to do this. But if you want to be smart, right? So I say that, okay, this is in the plane, X and Y, and in the perpendicular plane, which is on the radial directions here, I'm saying that this is in the C direction. So how the concrete dam resists the hydraulic force? So the hydraulic forces mean, you remember what you learned from your scientifics, right? The science that you learned for the high school science. They're saying that the hydraulic pressures that hit to the body, right, is along the depth of the water. If you're having the depth here, which is H, which is the depth of the water, the pressure underneath this is equal to the rho, which is the density of the water, which is 1,000 kilogram per cubic meters, times with the G, which is the gravity acceleration, which is 9.81. So we can approximate them to be 10, right? And time with H. So you got the pressures, which is starting from 0 and maximums at the bottoms, right? And we call them, this is the hydraulic pressures. The dam had to resist when you want to keep the water in the upstream of the dams. So it had to use the sail wedge of the dam, because this is made of the concrete. This is a concrete. So the concrete is got the density of, which is the density of the concrete, equal to 24 or kilonewton per cubic meters, or it is equal to 2,400, right, kilograms. So if you take, right, when we do the analysis, we have to see that how much of the water level can keep in the dam, such that the dam doesn't overturn. So when it's overturned, so it means it's just flip up. The water push to the face and flip the concrete dam up. So normally people, how they can check is, first, they're saying that they have to model this problem as a three-dimensional space. They're saying that they can approximate the problem by looking at the condition of the prop of the structure you're looking at. Along the axis in the C direction, we knowing that the strain that run along the line here equal to 0, right? Because it's so solid, very thick. The strain in the radial directions here, or in the perpendicular direction to the plane, that every slide that we made the cut through, it doesn't have the strain, right? Because it's so thick. And that's why we can simply model this problem as a plane strain by saying that, all right, the strain that in the perpendicular direction to the cut of the slice, we're looking at in the plane, including the shear strain as well, equal to 0. So we end up with the plane strain. If we having this, so I can just simply cut any section or any slice to what I like to investigate the problem. So I say, okay, I want to cut here. And I like to see how much of the dam, analyze the dam behavior of this cut. And I like to investigate, right, how much of the water level can rise up, right, and what is happened at each of the water levels, what is happened to my structures, right? So that's why I make the cut through. This is the slice of the plane stress, sorry, the plane strain that I'm looking at. So I cut through, and the problem we're looking at is here. Okay. So what we do, we call this part as a, this is the crest, C-R-E-S-T, crest, right, which is at the top, right, of the dams. And what the question, what they ask you is this: if I try to overload the dam, so I keep raise the water level, sit above the crest point, which is at the top level of the dam. I like to see how much of the stress and how much of the deformations that is going to be developed for the dam. So what we worry the most for the dam is that looking at the simple analysis, let me show you what the simple analysis and most people can do for the analysis of the dam or the design of the dam. You have the hydraulic pressures, right? This is a triangle where the water level is at this. When the water level start to be overflow, right? The amount of the overflow is alpha. You have the additional water level. Okay, so this is the hydraulic pressures. That's it came from what we saw that is it came from water, right? And once the water is rise up, what is happened at the corner of the face of the dam that have to resist the hydraulic or the water force, the water can penetrate through the dams, right? And when it's penetrate underneath the dam, it's trying to create the uplift pressure. So it's trying to push this area up. So we call this area as an uplift. The amount of the pressures here is equal to what I assume in this assignment. The amount of the uplift pressures, it is equal to the amount of the pressure at the bottom. So you know that the pressure is the force per unit areas, right? So you can approximate them by, if you time with the area, you get the value of the force. So I say that the amount of the water pressure at the bottom that try to push the dam to the sides, and this try to lift it up, right? The magnitude of them, they are the same, right? But this one, they form as a rectangle water pressure level and uplift. And this one, they form it as a triangle, and also some part become rectangle, right? The part that become the rectangle, this is come from the pressure that is overflow. Overflow is mean anything that sits above the top crest of the dams, right? So what we like to analyze a dam is this. I say that there is an opening. This is the opening at the corner of the dam. The value of the opening is equal to 5 meters, right? So you're looking at this equal to 5 meters. So this is opening. When it's opening, what is happened when I want to do the structure analysis, right? So it start to tell me the boundary conditions. What is telling me for the boundary condition is this. I know indeed that at the boundary lines here, it has been well connected to the ground. When it has been well connected to the ground, so what it's telling me is that when I'm looking at the node here, each of the node point is giving me the restraint condition, which is dx equal to the dy equal to 0. But the condition, anything at the opening, so it's freely. So the degree of freedom at the bottom has been free, so it can open up, right? So this condition is telling you, okay, in this case, you have this type of boundary condition. The length of the dams has been free. So the degree of freedom is can move in any x and y direction. So we start to know the boundary condition. We know what is the applied force, right? And another thing that you have to keep in mind, this is very important, because the only mechanism that can resist the hydraulic force is the gravity load of the dam. Because the dam by itself is got the Sawekchai. The Sawekchai, which is a concrete, is come from the density of the concrete. So I tell you the concrete density is equal to 24 kilonewton per cubic meters, or 2,400 kilogram per cubic meter. So that in total, we give you the resisting force. The resisting force that resists the hydraulic or the water pressure, the only one is a concrete Sawekchai, which is the huge. If you're looking at this, it's a huge matrix of the concrete and try to resist the hydraulic force that come from the water. Every time that the water level start to rise up, so it start to give more pressure and push the dam, right? And we don't want the dam to fail. The dam fail is means it start to open up. When it's open up more and more, it start to fail. The water start to keep penetrate below and try to lift this up until the dam overturn, so it's collapse, right? And we don't want that to happen when we do the design of the dam. And if we run the very simple analysis, I tell you, very simple analysis at what you used to do when you was the high school. Oh no. I'm saying that, okay, I try to give the boundary conditions here. So this one, I fix them. Right. And I know there is a force. So I represent the uplift pressure with a single force, and I apply them to the centroid. And this, I say that this is the uplift. And according to the hydraulic force, I have two types of the force. One is a triangle, which is if the height of the concrete dam is a h, the first hydraulic pressures will be around here. And the other hydraulic pressure will be at the half. So you have F1 at the upstream. I call him F overflow. F overflow is mean that the pressures which is in the rectangle, because is the pressure of this value is coming from the level that the water rises up, right? So that it creates this portion of the pressures. But this is upstream, so this is at the top of the class. So what I do, I can simply use the very simple summation of the area of the force. So this one here, I get the triangle areas. So I know how much of the water pressure at the bottom. I know how much of the overflow is in the rectangle areas. I know how much of the uplift. So I apply them to the centroid of the force. Then I simply take the bending at the support point here. I'm saying that the sum of the bending had to be equal to 0. And to prevent the overflow, right, we have to calculate, you see that each of the force, we make the overturning bending moment, right? Three of them, we've made the bending that try to overturn the dam. And we have to find the force that can counter wedge back. The way how we find the force that can counter wedge back, we have to decide and find at the centroid of the dams. This is, we call them as a cell wedge of the dam, and it's make the DD as a counter wedge or the counter force to make the dam to be stable, stabilizing. If you read in any type of the books that they suggest how you can simplify the problem of the dam, they say that you should very simple use these diagrams and you make sure that this force is good enough. They just keep saying that they make sure that this force is high enough to resist this type of the force. And if you're sure that the cell wedge of the concrete is good enough, so there is no such overturning going to occur, because you just make the equilibrium of the resisting force and also the acting force, so it doesn't cause you the overturning problem. In this problem, once again, so we want to investigate the dam in more details. So what we said in more detail, what it means is that we want to looking at the distribution of the stress in the dam, and we don't want to model the dam as a rigid body. This is called as a rigid body or the rigid dam. Why I say that it's a rigid dam? Because when we make the analysis like this, this is a simplified method, right? In the simplified method, we call them, this is the simplifiers. So in the simplified method, what they're assuming is this. So they're assuming that the dam, the body of the dam by itself, it doesn't deform. So it's just like a rigid mass, solid mass, very solid mass, and very strong. So when it overturns, so it's just overturned as a solid mass. So it doesn't deform at all. But in our analysis, we tell that the dam is not that rigid. It's like it's softer. It's softer than the rigid. So it's had the deformation. So if it receives a force, it can deform, right? You can see that the dam can deform like this. And they're just asking that in case that there is an opening, which is at the free edge, at the corner, it starts to lift up. So it starts to free, right? It doesn't ground it to the surface or the bottom ground and the bottom surface here. The only support that you have is only this distance. They're asking, how can you try to approximate the value of the uplift at the bottom? First, second, find the distribution of the stresses in the concrete dam, and you plot the deformation. So what I expect to see the deformation is you might see some slightly lift up here, and this is just grounded to the surface, and these start to bend as a cantilever beams. You might see the deformed shape like this. To be able to do this, we analyze and we model them as a plane strain. And when we analyze them, you have to use phono. But the phono that we have here is a bit more sophisticated, a bit more difficult. So rather than if we use the uniforms, so you can just model the dams by having this boundary condition as what we used to discuss before. This is the boundary of the dams at the crest point. And what I do, I just count right up to 5 meters, assuming it should be the distance over here. And the less of them, you just allocate the support condition. So in this support condition, so what you do, you restrain them by having the movement in X and Y equal to 0, right? And this one, you let it free as a free surface, right? You can simply allocate the node number, right? The pattern I suggest is you follow this pattern that I have here. So you can have all to be the rectangle. But if you're doing this, the thing that's to be critical, we want, right, when we want to investigate the problem, the thing is that at the location where we have the high value of the stress, which is more likely most of the cases at the support, we need to have the more number of the mesh to capture the value of the stress. Well, the more of the meshes you have, the more of the accuracy of the accurate stress that you can obtain. So if you use the uniform, this one we call as a uniform refinement, right? So you would need so many elements in the model, and that is very painful. So what I suggest is that you should use some type of the transformation. The nice thing of this type of the mesh pattern is as follows. Listen to me first. So if I'm looking at the problem here, and I just try to run the standard structural discretization, so I just keep dividing by half, right? So I had to keep, if I keep split by half, and I keep doing this. So, and I want, let's say that I want to investigate the stress values at the bottom, because I know that the stress value at the bottom is a critical. So what I need is I need more number of the mesh at the bottom. So I said finite at the support boundary. To ensure the accurate stress solution. Okay, and this is the the thing that I like to compare to you. So if I have this triangles, rectangle body, and I'm saying that, okay, if I want the more number of the mesh, so basically I want the more number of the node at the bottom to investigate the value of the stress at the boundary condition, because in this condition you have, listen to me, the continuous support, right? If you discretize them, so you have the discrete support at the node, it doesn't form the continuous support. So that's why the more of the mesh, the better of the results. So let me just rearrange more. You say this is continuous. And emphasize here. And this is to ensure right. So by doing this, if I want to keep as a uniform mesh, right? The pattern that I have on the left-hand side, I call them, this is the uniform mesh. So if I doing this, you just count how many mesh I have. It's a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So it's 4 by 4, you got 16. 16 mesh you use. But if you're doing according to what I try to do, I just simply subdivide them first. Let's say subdivide them by half. So I use 4 mesh now, and I try to use this irregular mesh. So this one is, we call them as a in a trapezoid shape, but it's still 4 node, right? So in this case, have a look. I could obtain the more number of the restraint point at the bottom. At the bottom, I just see how many restraint point I have if I have the uniform mesh. I got, in this case, at the bottom here, I got, this is a non-uniforms. Right, this is the non-uniforms. But by having the non-uniform, let's start to count how many mesh I have. I use here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I just use 10 mesh. But how many of the restraint point I could have, I could obtain? At the bottom, I got only 5 restraint point. But on the other side, I got 7 more, and I use less number of the mesh. That's why in this problem, I suggest you to use the mix between the uniform mesh. When we have the uniform mesh here, it means that it is a location that we guess the distribution of the stress will be uniform. When the distribution of the stress will be non-uniform, right? So it means the chain of the stress start to be increased and start to be a lot. So we need the more number of the mesh and the more number of the restraint point at the bottom line here, because the support at the bottom is a continuous line of the restraint. So we could not have just a discrete on the dot, otherwise you didn't have the accurate solution. So we need to have the more number of the restraint point on the node at the bottom. So that's why better to use, this is the transformations of the mesh, but you see the non-uniform mesh. Right, so this is the benefit of this. Just the way how we construct the mesh. The rest of the problem is the same, right? So I explained the concept, the idea, and how we come with the mesh and so on. I will upload these slides, this update through my course view as well. So what you need to concern is this. So you need the basic metric property, but you need the salvage of the structures. I will explain to you how, when you have the salvage, right? This is in the unit force per unit volume. How can you obtain the force as the, there is a function that you can obtain the force at the degree of freedom in the direction that you want to, right? And the gravity load is in the vertical direction. So what you do, right, you just read through the information and giving you as well, this is the hydraulic pressure. So you know already the hydraulic pressure is trying to push the force here, right, and make it in the unit of per volume, right? So you just assume the thickness of the dam to be the unit, which is 1 meters, right? Because this is in the plane strain. And what is the most important is the level of the overflow height. So each of the group, we have the value of the overflow height, which is the value of this height here to be different. So that determines the values of the stress in the block that I highlight here to be different. Okay, each of the group we have the value of the force in this rectangle to be different. The rest will be the same, right? That depending on how much of the overflow value you're looking at. Okay. And what we do is that the problem asking you, you analyze, you model the dams, you apply all the force, and don't forget the resisting force here. Why is it important? And you just find out how much of the displacement uplift at the corner and the stress distribution in the dam, right? So this is the third problem, and this is the most difficult one. The most difficult is how you modeling them and how you do this run to be automatic mesh generation, right? So the idea of how you simply the code, what I suggest, once again, you should try to count from the simple problem first, and you will see the pattern of the number. And you can use a pattern of the number, try to indicate how many mesh you want to discretize, and the connectivity can follow up. Before I move, sorry that I arranged the class a bit late, but because I got some of the class before, and next week we start at 3 as well. And we might run slightly over the time, so I try to finish for this lecture today by 5. But before we move forward to any question first, please. No. Everyone, I didn't see your feedback, so I'm not sure whether you understand well or not, but I'm presuming that you should have the what's it called, the basics formulations that you learned before, right? So this should not be new to you guys, totally new to you guys, right? Okay, if you don't have the questions, so let me start some of the recap, some of the equations we use. I don't have time. I don't think I have time to write everything on. So that's why I might have to take some of the note that I have before. So this is the note I will upload through my course view. It didn't come. Can you just hold on a second? No. No. Okay, that's fine. So let me write everything again. Otherwise, I might just continue on this. Easier. Good. There are a couple of the formulation that we use for the isoparametric finite element in plane strain. So, sorry, yeah, in the displacement fields. So we talk about this is the linear finite element analysis. I just recap some of the basic formulation. So we use for node, isoparametric element. So the form of isoparametric element, what it mean? when we looking at the isoparametric elements, the first thing of all, you need to know this is the geometry you're looking at. We have the square in terms of the element, right? And the coordinate of the element is we starting from x, y, and x, and we call the coordinate, this is the eta coordinate, and this is the cursive. Normally we use the coordinate in x and y, but when we do use the isoparametrics, so we want to use a unitless, that's why we call them as a unitless element. And what it means in this unitless can represent arbitrary forms of the element. For example, you have the arbitrary forms of any element. The difference between this mesh is that this is not good. Okay, this mesh is we have the informations of the node. And this is the physical mesh, so it's a real mesh. And it's got the coordinate of x1, y1, x2, y2. And this one is a x3, y3. And x and y is a coordinate. Right, and it's got the axis as well, and they refer to the Cartesian coordinate, which is x and y. The left-hand side, which is the real mesh, real geometry. And you can model this by using the 4-node quadratic element. Quadratic is a bilinear. And the right-hand side, we call them, this is the unitless or the dimensionless. And this is a 4-node isoparametric element. So what the difference between them is this. If you use the finite element mesh on the left-hand side, you can use some other standard form that you take before, but the problem is that you may need the time to prepare all the key matrix, right, which is more. But if you use an isoparametric element, they will treat all the mesh that you have here as a unit length. The unit length is mean you have the nodes 1, 2, 3, 4, and the coordinate you're looking at is a -1. You see that everything will be 1 and 1. So this is in the unit length. That's why we call them as a dimensionless. But in any arbitrary dimension, you always end up with a square mesh in the calculation. And this one is very nice. If you have this property, when you form the formulations, right, it's much simpler. To be able to satisfy this, so we want to transform, this is our real problem, which is on the left-hand side. We need to transform the left to be the right. And how we transform them? So we have to indicate the function. When we do the indication, when we call the isoparametric, what it means is that the shape function that we use, which is in terms of x function, has been written in terms of the shape function is n1. You learned the shape function already. And this is come from the displacement fields. And you can describe this is a geometry in terms of x1, x2, x3, and x4. In a similar fashions, you can determine the displacement. You can define the displacement in terms of the similar shape function. That's why they call them as a isoparametric element. Because they use the same shape function for the geometry and also for the displacement. We need this property to be satisfied first, so that we can transform the real geometry to become the dimensionless geometry. So we have the coded in x and y, right? So you just repeat them for in x and y. And we normally use the same shape function for the coded x and y, and also for the displacement in x and y as well. And the shape function we use is a bilinear. So we define the displacement in x direction as a u, and we define the displacement in y direction as a v. And v on the columns, what I'd like to show you on the columns here, this is the geometry or the coordinate at each of the real structures, right, that you're looking at. And this one here, which is the displacement at the node in x and y, right? So we have things, the displacement. This is a u1, v1, and so on. So we keep doing this. So once we have this property satisfied, the basic shape function, I can write it down for you, right? But let me. I hope I have more space. The basic shape function that we use for the bilinear, which is ni equal to, no, it's not enough. Then just hold on for a second. Let me just try to reduce the size. So we use the shape function from the dimensionless, which is a 1 subtract plus . Well, this is the shape function for the 4 node, and we use the shape function of this. The meaning of the isoparametric is both of the terms, they can be described with the same shape function, right? So that's why we use this. And the rest of this, I'm not going to derive the equation for you, but I just use it, right? Because I'm sure that you use it, you learned it before, right? The equation that we use, let me see where it is. Okay. For the governing equation that we want to construct, first, you have to construct what is called the stiffness K matrix. This is x by x for each of the element, right? Because you have 4 the node, and you may ask, okay, before we start with the stiffness matrix, I start with the force function first. For each of the element, this is the force. Where the force is from, you see that we have the displacement at each of the degree of freedom. At each of the node, it's got 2 displacement. So that's why U1 and V1. So that's why we have the force corresponding to the degree of freedom. So the dimension of the force vectors is x by 1 and equal to the standard stiffness matrix of each element, right? And you say here is x by x. And this one, I'm saying this is belong to the member I times the displacement, which is x by 1, belong to the member I. And we assemble them later. And to obtain the stiffness matrix of each member, so you need the formulation, which is in the double integrations. And what we use is that the standard formulation is a double integration along x and y. This is in the real coordinate of the matrix B. B is the first derivative of the shape function. And the size of them is 3 by x. And E here, this is called as a hook matrix, come from the hook clause for what we use for the plane stress and plane strain, which is 3 by 3. This is the constant matrix. And this one is a B as well. So when you take the transport, this will become x by 3. And when you do the integration, it's time with the thickness of the member over dx, which is over the area within the plane, right? So this is the standard stiffness matrix equation, that what you learned before. But this is, if you're doing this, this is the standard 4-node bilinear equation, the quadratic formulation. But what I like to use the isoparametric element so that I can derive the equation based on this square element dimensionless diagrams. So we need some of the transformations in the matrix. So we still do the double integration as well, but rather than we integrate them over the x and y coordinate, we integrate them over -1 and 1. Because in our isoparametrics, right, in the cursive direction, we integrate from -1 and 1. In the eta direction, we integrate them from -1 and 1, right? So that's why we have in these formulations. And all the matrix, and what we have here, they got the same description, but it has been written in terms of the coordinate of eta and cursives, right? So what I try to say here is that this had to be written in terms of the function of eta and cursive for both of them, right? Because we want to transform, use the different coordinate systems. Then it's time with the thickness, but we need to transform the coordinate, right? Rather than we use x and y, we use a natural coordinate. So we have to time with the determinant, which is the J, and decreases by dn. And how are we going to describe this term in terms of this, right? So we have to use, let me see. We have to use a description, which is in the third step. So I go deep down that, okay, the strain, when I define the strain, this is the standard strain function. So each of the element is got 3 of the strain values. So we having, this is a beta, no, sorry, the B matrix, and time with the displacement. And how I obtain, I just try to expand the forms to be large. So that's why I have this to be the epsilon xx. I have to write to be little. Okay. You can just bear with me for a second. So this is the standard definition of the strain. Right, and based on this diagram, so I can just simply write them in this form here. I'm not sure I have enough space. The term that I put in the green one, this is how we transform the coordinate, and we call this one is a I got the definition of them, so I will show you. Let me rearrange this first. This is the inverse of the Jacobian matrix. So that's I should put the note here. Determinant of the Jacobian matrix. Right, so I just shrink the size and I put in the box. This is the inverse of the Jacobian matrix to transform the coordinate. We use this term to transform all the coordinate that we want to. Right, and the last one is a derivative of the natural coordinate. So what I use in purple. Is it in terms of the shape function? It's very long terms, right? But please bear with me for some times. The reason why I need to talk about the formulation first, because this will involve when you're looking at the coding. So I just keep following this. For this is for the displacement in X. This is the displacement in Y of the node 1. And I keep copy this and repeat them in the pattern. But the only thing that I change is I just simply change. I have to zoom it in quite large. The shape function to be 2. Right, and I have to repeat this. Let me see, you have a space. Okay, and I change them to be the shape function according to the node we're looking at. So we have the node 3. And the last one is a node number 4. And this has to time with the displacement at and the coordinate, which is we have a u1, v1, so I'm sure that this one you might learn the basic formulation of this. So this is the one we use. Right, so we define the value of the strength. And what I like to emphasize is that the resultant of the multiple product of this will giving us the B matrix. And you have the dimension of them is 3 by 8. Right, and you can use this and put them into this one here. Okay, and we use the Gauss-Point integration rule. So I'm not going to emphasize what is meant for the Gauss-Point integration rules, because I think you may have learned before, otherwise it will take a bit of time. So we need this couple of the matrix. Once again, have a look. If we go to the step 1, this is the basic formulation we need in our designs, in our analysis, which is force, right, time with the stiffness matrix of the element, and this is belong to the element 1, element I. This is belong to for each generic element. I. Right. If you have 100 elements, 1,000 of the elements, so you have to construct the matrix K for thousands of them. Okay, and this is for how you want to obtain when you have the double integration. So we use this isoparametric element, right? So the integration that we use a Gauss the 4 point of the Gauss point quadratures, and you just need to define what is the B matrix, which is the derivative of the shape function, and it's been derived into these equations here. This is a transformation. This is the inverse of the Jacobian matrix, right? And that can be written in terms of the unknowns displacement at each of the node. We have 4 of the node, right? Remember, we have 4 of the node here, right? We transform this geometry to become this geometry. So the displacement will be at the node 1, u in x, v in y, and we keep running the displacement for 4 of the nodes, so that you have 8 of them. And if you can obtain this, basically you just have the K matrix and you assemble them according to the degree of freedom. The matrix K for all finite element that you have, right? Using the information at the degree of freedom. And then you can obtain similar to what you did for the stiffness method, right? And you use them to assemble to obtain the K matrix without I, right? This is the one that we need the most. And you need to assemble as well. Similarly, you assemble for the force. Force we use RE, right? For all, then you obtain so by having this, you can have the governing equation. This one can be run and use it for all elements. Okay, I think I run quite a lot of times, and before I talk a little bit on the code. Anyone have a question on this first? I'm not sure whether I recap so much or not, but I try to bring out all the equation that we use first before we go ahead. Right, and this is the equation we take. And how can we do and how can we solve and put into the computer codings? So let's just bear with me for a second. By giving you guys the codings, it is a package for all the coding. Hope everyone sees here. You can see that there are around 1, 2, 3, 4, 5, 6, 7, 8 of the MATLAB coding. So each of them have the different purposes. So what I like you to do, you should start it from, this is the input files. Have a look here first. Every time when you want to run or want to use the the CALFEM, it's got the different of the module that link together. And the module that I pick it for you, this is used for the purpose of this assignment. You don't need to develop anything new. You can use a module that I have here. The main module is called as a FE bilinear. The FE bilinear is used for the calculations for the standard four node isoparametric element, and they assemble all the matrix and the vector to what I told you just before. And if you have a look here, I have put them in the different framework, starting from the input files, which is according to what the input you want to have. You have for the structures, you might name them to be for example, the structure A, structure B, structure C. Every time when you change the structure, you just change these input files. The rest of them, you keep it as is, and that will perform and construct the matrix Ki, Bi, assemble the global K matrix, assemble the force matrix for you, right? You just need to have this to be correct. Before we look at the input file for brief, I'd like you to look at the way how the code is worked. We have the parameter initialization, so that define whether it's a plane stress or plane strain. P type, I think, equal to 1 is a plane stress, equal to 2 is a plane strain. T is a thickness. I are, they are the number of Gauss points. We use 2 by 2 Gauss point. You should put 2, not 4, right? Because the standard Gauss point, we use 2 Gauss point, but we have to do double integration in X direction and in Y direction. That's why we said 2 by 2 equal to 4 Gauss point. But the standard Gauss, we use just 2 Gauss point. Okay, don't be confused about this. The node, they just extract extract the number of the node for you, right? According to the input, you have to put the coordinate. If you recall what you did in the advanced structure analysis, I try to use the same notation. The coordinate, you just input the coordinate of all the element. What I suggest is you try to use run the number of the coordinate in a series number. So that's why when you want to discretize more the structures, you can do it automatically by using some of the little piece of code that you can write by yourself, right? Similar to what I show you for the structure A. The EDOF, this is giving you the informations on a number of elements, right? So how the connectivity is work, I will show you in the input file, but I use the same notation as what you did for the for the trust analysis and the frame analysis before. And the maximum degree of freedom, they read information on the DOF. DOF stands for the degree of freedoms. And the rest of them, they just keep extracting the size, the dimension. You see, number of Gauss point is IR by IR. This is the 2 by 2, right? We use the standard 4 node, right? So each of the element is got 4 of the node. That's why it's time for. Then they start to assemble the K matrix. So they just open the array of the size of the K matrix, which is the 0 by 0 in the dimension of total degree of freedom by total degree of freedom. And they start to call the hook. This is the hook loss, right? This is the standard plane strain and plane strain. So they start to assemble the D matrix for you, right? And how you find this, you just go to the hook. You see, this is called as a hook function. They just go to the hook. And each of these will giving you for the member at the member level or the element level, the hook equation. So if you go for 1, this is the plane, right down here, this is the plane stress, this is the plane strain. You can have the anti-symmetry, you can have the 3-dimensional, which is the full function. But we only use for type 1 or 2, right? This is done, so it's just bring it back. Then you start to run the loop, right? I think in this one here, they use, listen to me carefully. In this one here, they use the uniforms, the homogeneous material member for the whole structures. So that's why they call the hook law for once, because they assume that for the whole structure, you look at, you have the similar elastic properties, such as the Young modulus and the Poisson ratio. In the case that you have to analyze the different properties, you have to separate, right? You have to change the equation for the hook when you have the different type of the material property. Keep in mind on this, but the assignment that you have in hand now, it doesn't have different material properties. I used to give the different material properties in some of the years. You have to adjust this, but I changed it for this year to have the homogeneous materials. And the rest of them, they start to call the loop. The loop here, they try to reassemble. If you recall to what the step number 3, number 4, I say that you have to construct the K for Ki for each member, and you keep reassemble them by using the information on the degree of freedom. So this is how you assemble the K matrix by finding the Ke. Ke is for each of the member, right? So each of the member, how you find this, the Ke, you remember the very long formulation with double integrations of B transpose times D times E times D, right? Times B, right? And with the Jacobian and so on. So these have been given and have been written in the course as plan I4, right? I is standing for isoparametric. 4 is a 4 node, is an elastic. So when you just need to have the input ready, they need the coordinate XY, they need whether it is the plan, I'm not sure EP, I think I wrote it down here. The EP is a body force. In case you have the body force, of course, for the structure C, we have the body force. So you just tell in X or the Y direction. So it will extract the force function for you. Right? Remember, the force function is equal to the integration of the shape function transport time to the force, and you integrate over the volumes. Right? I will write the formulation down for you. And it will extract the K for the element. Right, and if you go through the process, they start to find the Gauss point first, and they start to find the shape function. They find the derivative of the shape function, and they find the Jacobians, and they start to assemble for each of the B, the shape function, and they form the K for you. You see, this is the K function, which is the B transpose DM is the Hooke equations times the and determinants of the Jacobian matrix times with the weight function times with the thickness, and they just keep accumulate for 4 times because you have 4 of the Gauss points, so you have to sum up to get the K for each element and the force as well. After you get K, E, you get F, it will return back to this platform again. So they recalculate and they keep assemble for you for both the K and for both the F for you, right? And after that, the process is easy. You just take the inverse of the stiffness matrix, you get the displacement. After you get the displacement, you just allocate the displacement to each of the element, and you use the equation number 3 that I wrote for you to get the strain. If you get the strain, you get the stress, and you can extract any value to what you want to. And it's coming with the drawing function as well. I give you the standard drawing function, right? So you can have a look here. I can try and test on this. The way how it's worked for the Cook problems. Sorry, I have to type FE bilinear. So it's we process and we generate all the metrics for you. And this is the Hooke equation. And this is the picture as what we're looking at, right? And it will also plot the deformed shape for you. If I just scale them, right, similar to what you did for the structure analysis, and you scale and you see that you have the force here and it will deform. We have the boundary constraint. We try to clamp or fix the coded in X and Y, right? So the cost more likely give the description, is ready for you to use. But what I try to emphasize in the beginning is to explain the problem, explain the formulation, and now we have the code. The thing that you need to know when you change the problems, you need to put having the new input. The input is very straightforward. Listen to me first. This is the Cook law, so I put the names, right? The Cook law, you see the geometry already, and I wrote it for you in the note. And I say this is the plane strain, which is equal to 2 Gauss point, the thickness, the Young modulus, the Poisson ratios, and what is the most important, you have to tell the connectivity of the topologies. The first columns here, listen to me first. This is the first column. What is tell you? This is the element number. We have 16 elements as an initial element. And this is the connectivity. It's telling you the node connectivity is start from the node 1, 2, 7, and 2. Sorry, 1, 6, 7, and 2. 2, 7, 8, and 3. So this one, you have to key it by yourself. Or if you don't want to key it, you have to write a little piece of code to keep refining the mesh for you, right? So that you can get the more accurate result. Remember, the more of the refinement of the mesh, the better accuracy that you can have for your solution, right? So each of the node, excuse me, it's got a degree of freedom, right? When I put it 0, 0, so it means I clamp them, I fix them, right? So it doesn't allow them to move in X direction and in Y directions, right? When I start to run the number of the degree of freedom, so what it means, I try to allocate the movement to each of the nodes. So you have to count, this is node number 1, 2, 3, 4, and run the number down. The coordinate is belong to, right? This is the real coordinate belong to the node number 1, 2, 3, and 4, and so on. And this is the force. You have two other choice. One is you want to generate the force by yourselves, right? Some say the example number structure A and B is easy. You can just calculate the point load for each of the node that you have when you discretize the problem. But the problem C is a bit more difficult because you have the body weight inside the dams. So you need to use, listen to me first, you need to use this formulation, right? Or you use this. When you use this, this is to generate or to construct automatically for you the force from the body force to become the force at a specific degree of freedom you're looking at, right? You go and have a look here. I might come back and talk about this later. The rest of the code, for example, this course, once you have the displacement at each of the element, you can recalculate back the stress values, right? So I define the parameters here, and this is the post star. I think you can have the stress values. ES is a stress value and the strain values. So you can use this stress value for each of the element to calculate the wall meter stress, right? And so on. So what I like you to do for this week, I like you to try to set up the initial mesh first for each of the problem you're looking at. Right, we have 3 other structural problems. You construct the initial mesh and you try to run it. Right, the most difficult one is the structure C. You have to use the body mesh, and you have to use. Let me show you what equation you use for the force function. This is not new. Basically, you have learned most of this before, right? If you want to obtain the force function, the formulation that you use is that you want to construct the applied force at the degree of freedom. And we call them, this is the matrix of RE. And how are we doing this? If we have the force in the boundary, on the boundaries. So what it really means is that, please bear with me for not too long now, please. We have, this is the node 1, 2, 3, and 4, right? And I start to define the force of this in terms of the functions of Qx and only through the distance of x. And what I want is that when we do the finite element analysis, we could not, of course, we could not determine the force by having a function. We had to provide the force at the node and in a certain degree of freedom. And how we can obtain this is that this is what is happened, and this is what we want. We didn't want this type of force. We just want to obtain the force.
Just wait, Chan. I think you
Yes?
forgot to share the screen.
Oh, I forgot. Oh, I'm sorry. I didn't share the screen. Okay, thanks. Not this one. Okay, let me just quickly explain to you. We want to obtain the force function, the matrix of the force, but what is happened in some of the case you have the function of the force in terms of the distance x on the boundaries, right? What we want is that we didn't want to have the force as a function, but we want the force to be described in terms of the nodal force at the node. And in this case, we're saying that the force will act in the y direction, right? And we're assuming that the force is positive according to the location, the direction of the degree of freedom. So this will act allocate to the force, the vertical force at the node 3 and 4. And how we obtain this? So in order to obtain this, we have the formulation, which is we use a standard formulation. Right, I write the standard formations down equal to the integration over the volumes, right, of the shape function. You may have x and y transport, and time with any function of the force, you can have the q in terms of x and y, and you just integrate them over dx and by dy, right? And this is the standard formulation of how you can obtain the transform the force functions here to become the nodal force. So what we do here, because we need to do the integrations now, the way how we do the integration, we do the integration over the line here, okay? So that we're giving me, this is what I want to, is we're giving me the standard information or RV3, RV4. I use a specific shape function along the line here, and I take the integration over negative a to a, right? Because you're looking at this is the, let's say the coordinate, you look at the coordinate, I didn't put the coordinate here. Let's say it's negative a, this is b, this is a, this is b. Right, just a standard coordinate that we use in deriving the finite element equations. So you just take the integration, but in this case, because it lies in the x direction, so you don't need to do the double integration, and you use the Gauss quadratures only 2 points, right? Which is the x transport times with the qx and dx, and you obtain this, okay? And what is happened if you need the body force? And if you have to apply body force function, but now is on XY body, right? So this we cover for the whole which mean is covered for the whole bodies. So I have to copy this and place it here. But rather than we have these equations, we saying that the whole body is got the force in the y directions again, right? In terms of the functions of the bill x and y, right? Then what you do, you have to do double integrations. Sorry, in x and y. So it might not be. I just said it might go to two directions here. But if you want them to go specifically to some of the directions, you can do so by reduce the terms to what I'm going to write them down. Let me copy this. This is force 1 and force 2. Force 1 and 1, sorry. This is a 2. So what you do this, you take, I don't think I have enough space. U1. Right, this is the alternation between U and V. U is a force in X, V is a force in Y. Right, and then you're just taking the double integration from negative B to B, negative A to A. And this is the standard formulation in X and Y. Take the transport and you have the W in terms of X and Y times dx dy. Right, and don't forget if you use a natural coordinate, you don't, just keep in mind that you don't forget to transform, sorry, using the Jacobian matrix, right? If you use a natural coordinate, you have to change this, and you have to transform this matrix by using the Jacobian matrix. But you don't need to code this up. It's giving you the coding already. It's not just telling you the concept, right? This you can calculate the body force. In some of the problem, this is a bit straightforward. For example, rather than we if you have a constant, if you apply the force with the constant uniforms, and this is a W, which is, let's say, Q equal to the uniforms 10 kilonewton per meters, and assuming that the distance that you're looking at. Just make it simple, 1 meters. You can approximate them by, you don't need, I don't think you need the integration by using the the shape function, because it is the bilinear anyways. So the way how it works in this case, so what I suggest is, if you have a very simple case like this, you just simply use a tributary area concept and subdivide the loading according to the areas, the length that is covered. Right, for example, in this way, it's covered according to this length and so on. So that's why you will have the force. This is twice of this. In the middle is a twice. And you have, let's say, this is 5 kilonewton. This is 10. And this is 5. This one is allowed it because we use a bilinear shape function. You can prove if you use a bilinear shape function and you use the full integrations of the force, you will obtain the same results. The only problem is you have the body weight. The body weight is different, right? So you have to looking at this. And excuse me, I think we have done so much over the time. Before I finish my lecture, anyone have the problem or the question first you want to ask? So what I like you to do is, yes.
ครับก็คือการบ้านของเราก็คือใช้ตัว CALFEM ทำได้เลยใช่ไหมครับไม่จำเป็นต้อง formulate MATLAB มาใหม่ใช่ไหมครับ
ไม่ต้องครับไม่ต้องครับก็ใช้ CALFEM เลย so okay the question that
refine mesh ด้วยไหมครับหรือว่า
refine mesh ต้องทำเองครับ refine mesh ต้องทำเองเดี๋ยวอาจารย์พูดให้ฟังอีกที
โอเคครับ
Okay, we got a question that your assignment, do you need to record this? The answer is no, you don't need to record anything on this. The only thing that you need to do, you have to generate the new input files. What I like you to test in this first week, I like you to try on based on the code that I provide to you guys and the formulation that we have. The code we use the same formulation as what we described here. And to try to construct the model or the structure A, B, and C with any size of the elements. You can use any size element, it's fine, provided you can obtain the results, right? So I want you to construct the mesh input by yourself for each of the group. We have 4 people in each group, right? And you can use any size of the mesh, the refinement, and so on. The first thing, the most important, you have to test it and you make sure that it's work, right? Because the rest of the formation is sound. So you see the concept, after you have this, everything will be automatically from the line 22 down to the bottom line, which is we have only 95 lines for the finite element code here. It's work. You just need to get the input done, right? And you have to read through the input, and I will write it down for the input file of the cook, what the meaning of this when we have this. So, and you can compare it, and I will upload to the course view this week, right? And later on next week, when I come back and meet with you guys, I will check whether you had a problem in generate, to use a code for the structure ABC. The only problem that you have is structure C. You need, more or less, you need the irregular mesh, which is a non-uniform mesh, to get it so refined to the bottoms at the support. And you need to get the force, the resisting force, as the body weight of the dam, of the concrete dams, right? So the formation that I just tell you, and this also been told in this coding. You can use this coding to generate the body force for you. You can put the plane I isoparametric 4 is a 4, not F is a force, right? It's give you notations here, and you can try and play whether you can use this code to give you the force matrix or the force vector. If you can have, you just extract the force vector and you can just append them at the bottoms here, right? And you just append them here. And or you want to write a little piece of code and call the function, which is a plane I for F, And every time when you call the input, they will generate a false for you. You can do that as well. And next week when we meet, I will start to talk about how we ensure the accuracy of the finite element, because the finite elements require the fine mesh. The fine mesh, you need to have a sufficient number of the mesh to make sure that the result is converged. Then we will talk about that. Should be short. As long as you understand the formulation, you understand the models, you understand the coding, I think you should be fine. All right. Any problem? Just feel free to ask me the problems. Every year, I tell you, I used to teach this framework. Let me stop the recording. It's good.